All right, let's get started. So we continue down this multi-objective genetic algorithms. Just as a reminder, the goal here is that we seek an evolutionary approach. So that's a population-based approach. Which ends up being natural for this, to generate a community of, and I want to say, effectively equivalent optimizers. And what I mean is, in the terms of us, not as domain experts, but as optimization experts, then these are, each one of them is a decent choice. So we have to have a domain expert to actually choose which one that they want. So that's what I'm going to say, effectively equivalent optimizers distributed across, and I will say the niche space, and so I'll explain kind of what I mean by that, which ends up being sort of the space of all trade-offs. Sort of hand wavy. So the basic idea was if that I had two optimization objectives, just because it's easiest to draw. Say F1 and F2. And let's just say that I would like to maximize both, or in other words, it's good for both of them to be higher. So wherever I am, it would be better if I was at a solution where at least one of them was higher. That's what I mean by a multi-objective problem. So this is the good direction, and this is the good direction. Then I know that I'm going to have a set of bad solutions or inferior solutions. And I'm going to have a set of impossible solutions. So that's the ones up here, this is impossible. And at the edge of this inferior solution space, there will be some boundary on which I can imagine a bunch of different solutions distributed across that boundary. And we refer to this boundary as the Pareto Frontier. And the particular solutions, so I'll say maybe abusive notation here, the set of solutions is the Pareto efficient set. And we can think of these all as being equivalent in that they all achieve dominance of all of these solutions down here, but they do it in different ways. And so this solution does it by providing more of F1 while less of F2. So it realizes a trade-off between this F1 and F2. And so you might have a particular domain area where F1 is more important to you than F2, but F2 is still somewhat important. In other words, if you could do things at a particular level of F1, then you had a choice between a lot of alternatives, it'd be better to do the alternative that was also good in F2. And so this captures that trade-off space, and we can kind of view the grouping of all these together as this community, using kind of an analogy from community ecology, and that each solution that we find inside these little segments, we can think of as being optimizing within this niche. So I would maybe refer to each one of these things as a niche. And so ideally, I would like to have solutions distributed across the niches. So in ecology, we have a community of things that live together. So these optimizers live together in the space of things that our stakeholder is happy about. And so we would want to distribute across that and say, these are all of the different ways in which you could implement your particular solution, but some of them trade off in more of one thing and less of another. And so each one of those we view as a niche. And so up here, this is kind of the best optimizer for this niche, and then we can go down through and think of different niches here. And so it's almost like the solutions are competing to find their own niche, and then once they find their niche, they're on the frontier and they're fine. They'll be in the community. So these niches are different ways that you can participate in that community. And so our goal as optimization algorithm designers is to find a way to prune away all of the bad solutions in such a way that we get rid of the diversity sort of in this direction, so everybody collapses to the community, but we enhance diversity in this direction so that we actually get the spread across the whole community and hopefully get a uniform sampling of that whole community. It's, we could get an outlier here and then a huge clustering here and an outlier here. And we don't want that because that might give the impression that the Pareto Frontier has gaps in it. And it really might have gaps in it. But if it doesn't have gaps in it, we really want to try to sample from the entire frontier. And that's our goal. Yeah?
Could you just remind me some of the industrial applications where these niches start showing up? Like in terms of delivering something to a stakeholder?
Well, so a simple example is that rather than don't even go in industrial, I can just think about you're making a choice of a particular product and you're a purchaser. So this could be you as an individual choosing a car to purchase, that could be me purchasing a piece of capital equipment. And you're always going to have to choose between things that have a certain set of features and a certain cost. And so you might want to minimize your cost, but you know that as you minimize your cost more and more, eventually you're going to give up on some features. And so it would be, if somebody gave you two options, one that was expensive and only had one feature, and one that was cheap and had one feature, you would not be blamed for buying the cheap one with one feature, but you would be blamed for buying the expensive one with one feature. But if you had the money to buy the expensive one, you probably should buy the one with lots of features. Now, I can't tell you how many features you need. So for your particular application, you might need all 12 features, but I'm saying that this is sort of the optimal way. This is like the market line, which tells you kind of like, what's the dollar amount I should associate for every one feature I want to add? And so the slope of this thing kind of tells you the market value of adding a feature. Okay. So that's what we're aiming towards here. So this is a very different way to think about optimization. It's this set-based way to think about optimization. But we'll make sure we're all kind of clear on here that we're looking for a community of optimizers, and in our minds, anybody from that community is good, and it's up to some other approach. So, and that, you as a data scientist, for example, you might then have to then take this and then figure out how to prune it further down using other methods. But at this point in the process, we're just trying to figure out how to do the first pruning to get onto this line. So make sure everybody's on board with that. Multiple objectives, looking for this line. Pareto Frontier, Pareto efficient set. Okay. All right, so then we started introducing different methods for doing this. And so last time I went into a lot of detail. I'm not going to go into as much detail. I'm just going to remind us of the three different methods we went over, and then introduce the next method here. And what I really hope that you'll take from this, the kind of concepts that you might be tested on, or I'm hoping that you'll take out of this afterwards, is that there are these three different sort of families of ways to approach this search problem, searching for this set. And they are just sort of, they're just qualitatively different. All the details for how you implement them kind of vary, and you'll find a lot of different examples out there, but the ones in these kind of groupings all kind of share a lot of properties. And so the first case we had were these weighted sum approaches. So this is kind of generation one of multi-objective population-based optimizers, or Pareto optimizers. And these weight-based approaches basically are kind of doing, if you know from another optimization class that for a convex Pareto Frontier, all you have to do is take a convex combination of your objectives and maximize that thing for weights, going from 0 to 1, and you know that will then trace out the convex Pareto Frontier. That's what these are kind of inspired by. And so the idea being here, like for example, the weight-based genetic algorithm for multi-objective optimization is this idea that we just make the weights part of the chromosome. So for every individual, make weights part of the chromosome. And so every individual has a set of weights, W1, W2, all the way up through however many objectives we have, that sum to 1, or if you want to, you don't have to do all K, you can do just K minus 1 of those, because there's only K minus 1 degrees of freedom here. And those just become part of that chromosome, and so they get mutated, they get crossed over. So it's almost like every individual not only has its own strategy, but it's on its own way to evaluate its own strategy. And so that was kind of the first approach here. And the nice thing about that is it's relatively easy to throw this into a standard genetic algorithm, because you just augment with these funny things, and then when you evaluate the fitness objective, then these chromosomes just get, so you end up having a fitness objective that looks like this, like F of the chromosome is just going to end up, you're going to break that apart, and it will be like W1 times F1 of whatever I'll do, the chromosome minus the weights. So that's my kind of game theoretic notation here, the minus weights, plus W2 times F2, the chromosome minus the weights, and so on. And so without any modifications to a genetic algorithm, you can immediately implement this. And that's the reason why these were sort of one of the first approaches. So relatively simple. So does that make sense? Any questions about that idea? Just add the weights to the chromosome and let things roll. Okay. Yeah.
It's not the equation that the weights are not part of the chromosome because it's contributing to the fitness function.
Well, so that's a good question. So this F fitness function here is your own. This becomes your singular objective, and so it's, as far as the genetic algorithm is concerned, this is a one objective optimization problem. And so and this big F isn't the fitness that I was talking about that kind of gets implemented implicitly inside. This would be passed explicitly as my single objective. And so this is I might call this, F1, meaning it's just like I created a fictitious objective that is a weight-based combination of the objectives that I actually care about. And as far as the genetic algorithm is concerned, it doesn't know any about this stuff. It just says, oh, you want to maximize this thing. But it just so happens that there's this weird structure that when I put individuals in and most of their chromosomes match, except for this tiny little tail portion, then the fitness is wildly different. And so we're just making the scaling of these sub-fitness functions, which the genetic algorithm does not see. It only sees this fitness function. All right. Yeah.
The small f1 is one of the objective a specific population, like a specific objective?
All the specific objectives are here. So these are your multiple objectives, which you care about. But you pass into the genetic algorithm, this is the GAs, this is a standard GA's single objective. So you code it up with a standard GA where the single objective just happens to be the weighted sum of your multi-objectives. But the single objective, as far as the GA is concerned, it's just a normal GA.
Well, aren't certain objectives adversaries of each other? Aren't they against each other sometimes?
That's the idea, is that these could be, this F1 and this F2, they may be identical, they may be different, they may be in agreement, they may be in disagreement, But the point is, this is motivated by the idea that regardless of what the mixture of objectives are, if these objectives are convex, then the convex combination, like if you were to say maximize W1 F1 plus W2 F2, where W1 plus W2 is equal to 1, this, if you sweep over all the different combinations of W1 and W2, will end up finding the Pareto efficient set if F1 and F2 are convex. They might be the exact same function, in which case this will just find a single point. But if they're different functions, then sweeping across all of the combinations of W1 and W2 that have this constraint is going to find that. And so it doesn't matter whether they're in agreement or not. This will find the Pareto efficient set. It may be a boring Pareto efficient set, but this will find it under the assumption that F1 and F2 are convex. And that's going to be one of the downsides of this approach, is that it doesn't work well when F1 and F2 are not convex. Yeah?
Are all of the weights positive?
Yes, right. All the weights are assumed to be, I could put that in here. So when I say the term convex combination, all right, so this is like optimization baggage. But the term conical combination means a linear combination with positive weights. So like if I have W1 X1 plus WK XK, and all the W's, Wj is greater than or equal to 0, that's a so-called conical combination. A conical combination with the additional constraint that the sum of all the Wj's add up to 1 is a so-called convex combination. So if I use that term convex combination, that's all I mean. The weights are positive and they sum to 1. All right, so that's the basic one. So simple, you can just take a standard GA off the shelf, code it up a little bit differently, and that GA will do an okay job at finding your Pareto efficient set. Sure. So that's our class 1. Well, that's the first member of our class 1. Now, that was kind of one of the first ones that came out, and then people realized that, well, maybe there are more interesting ways that we can do this. And so still motivated by the weight-based approach, then the other kind of subclass of this weighted sum approaches said, well, let's just modify the GA a little bit, and let's actually give the GA all of our multiple objectives. But then when we come around to the selection step, we're going to randomly draw the weights. So we randomly draw them in one generation, and then we evaluate as if we had a single objective. And then the next generation comes around, and then we randomly draw them again with a different set of weights, a convex combination, and then you do that over and over again. So every generation has a different balance of these. And so that's the so-called randomly weighted GA. And so we choose random weights, W1 through WK, where they're all greater than or equal to 0, and they sum to 1. So you can draw, if you're clever about it, you can draw basically k random numbers and normalize them. That's one way to do it. There's a bunch of other ways, but you can draw a random combination, and then then at the selection step, then use those random weights with the kind of like temporary objective, or I'd say generation objective, that's just the combination, W1 F1 plus WK FK. And typically what RWGA does is not only is it doing this, but they said, well, let's also extend elitism a little bit and realize that occasionally we're going to find non-dominated solutions this way. And whenever we find a non-dominated solution, we should keep track of it. So typically, they also, in parallel to this, maintain a set of non-dominated solutions. And this is sort of the Pareto equivalent of elitism. So the idea is, like, I end up finding, I evaluate a solution and I know how it works in F1 through FK, and then I look at all my other solutions and I know, and I've saved. So that's the thing, is you usually would save these evaluations. So maybe you keep another variable called Z, and that way if it's costly to evaluate this objective, you then store in memory the pairs of the strategy and what the objective is. And then you can quickly go through that and say, does my new solution dominate any of my previously non-dominated solutions? And if it does, I get rid of the ones that I now dominate, and I update this set. And so initially this set is empty, then through the first generation you come down through here and you might have 100 solutions, but 98 of them are dominated by the other two. And so the other two are better in both objectives than all other 98. But the other two, one is better in one objective and the other is better in the other objective. And so those two are the non-dominated solutions. So I save them in this set. Then I can run this whole generation again, and I keep them in that set. But then maybe now in my second generation, I have a new set of non-dominated solutions. And maybe now those non-dominated solutions dominate my previous non-dominated solution. So I have to update this set. So I run this over and over and over again, and then this set that I'm maintaining is going to be my community of my hopefully Pareto efficient solutions. Yeah.
You're generating these weights randomly, though.
Every generation, you generate a new set of random weights. That's right.
Could you find a way of like seeing a pattern as like a solution, a dominated solution or dominating solution has a pattern of where maybe the weights are being assigned, and then incorporate that pattern in to increase your frequency?
So some sort of like gradient ascent on the weights or something like that.
Yeah, just to improve your chance?
I mean, it's possible. I mean, so RWGA was pretty old, and so it was back when the hardware available was, I think they were trying to keep things a little simpler, but there's probably ways you could do that. I think the kind of the most recent generation of multi-objective genetic algorithms kind of beats a lot of these anyway, and so you probably wouldn't go this route, but if we were still stuck in the kind of weighted sum approach, then yeah, that might be a more modern way to enhance these, or at least investigate. Yeah, question that was far back and then the front. So first.
So I have, let's say, F1 to F5, like five axes on which I'm trying to optimize. Now I want to know, like in programming, how do I get the notion of non-dominated into a code? For example, it's very tough to get a solution. Like, I understand what it means. Like, I'm doing well on all 5 domains. Somebody else is doing well on 4 domains. I'm dominating him.
Mm-hmm.
But is it like a pairwise thing that you pick and compare, or how do you know
Yeah,
that somebody?
excellent question. So if I have, let's not worry about how many objectives, but well, for now, let's say I have 5 different solutions, or maybe to make it easier, it'd be 4, and each one of them is got Z1 is equal to it evaluated at F1, and it's got Z2 is it evaluated at F2. And so each one of them have got a Z1 and a Z2. And then you can kind of think of putting a predicate here of saying, is this dominated by anyone else in the set? And so if you were to do all pairwise combinations, you can say like, all right, so let's say I look at, I could put hard numbers on this. So let's say I'm just going to create random numbers here, and hopefully this ends up being interesting. So maybe this will be 5.5, this one will be 3.3, this one will be 1, this one will be 7, this one will be 1, this one will be 9. And so I now can like imagine a column here, and I can say, is it dominated or not? So does something else dominate it? And so if I look down at Z1, I can say, all right, I'm going to start at Z1, and I'm going to search through this list. And I see that X1, well, for X2, Z1 is greater than, this Z1 is greater than this Z1, and this Z2 is greater than this Z2. So in that case, I say, yes, that is dominated. And it basically means that I am going, this one is, there's no way this is making it into my non-dominated set. And so you can do that over and over again. And the first time you find that something's dominated, you can stop your search.
Okay.
Now you could imagine you could probably build some interesting data structures that would make this more efficient to calculate so that maybe you don't have that n-squared complexity. But for all intents and purposes, you could imagine with n-squared complexity, you compare every pair. For every pair, you get a winner. It's kind of like tournament selection. And if you find that that there's going to be some solutions which never lose, and those are your non-dominated.
Okay.
Okay. Yeah, sorry, question in the back?
If the weights are random every time, what's the point? Make them random every time. For example, for first round, W1 is 0.9, second
Yes.
round is 0.0001.
Right, right.
Then the second round, my F1 is becoming 0. What's the point?
Right, so the idea here is that if you kept them all at one weight, you're going to find a single point on the Pareto frontier. And so the thought is that you're trying to put pressure on the solutions to be attracted to the whole line as opposed to one point on the line. So if I were to flip back and look at this graph back here, then this, maybe I shouldn't choose that color, maybe I'll choose this color. So a particular point on this line is going to correspond to a particular set of weights, like 0, maybe this is W equals, in this one it looks like I'm maximizing more of F1 than F2, so maybe I'm going to make this 0.6, and the other one, W2 equal to 0.4. I don't know how readable that is. Okay, so the idea here is that here I care a little bit more about maximizing F1 than F2, which is why instead of my solution being right in the middle, it's slightly biased towards F1. So if I were to use just these weights over and over and over again, my genetic algorithm would end up finding points around here, but it would not spread across this. So the idea is that if I randomize these weights every generation, then I am putting sort of a dynamic selective pressure where you can imagine I keep attracting my search to different parts of this line. And the hope is that I never quite converge on any particular point and end up spreading solutions out. So some solutions end up sort of being, happen to be more F1 optimizers, some happen to be more F2 optimizers, some happen to be in the middle. In reality, what often will happen with a lot of these approaches in these first two classes is you get a cluster of solutions here and a cluster of solutions here, and you don't really get a nice spread across them. But you do get some dispersion, and that was kind of, but that's the idea. I'm randomizing this to provide dispersion across the line.
What are being optimized at the end?
What is being optimized by the end? Well, if you want to think about what's being minimized is the distance between the points in this line. So we don't know where the line is. So that's kind of, this is sort of a heuristic that helps ensure that you've got progress toward the line. Yeah.
In this case, like, how do we terminate the process?
Yeah, excellent. So how do you terminate the process? So you have to come up with some termination condition. You either do it a number of generations, that's an easy one, or you could do it based on some convergence criteria. I happen to notice that my non-dominated set has not changed in the last 5 generations. So if my non-dominated set is sort of converged, then it's probably unlikely that I'm going to find any more, so I can stop.
One more question. So when you were talking about the frontier, Pareto frontier, you said line, is it necessarily a line or?
No, it's for 2 objectives. It is something of dimension 1, but it is not necessarily. I mean, it could be kind of a wave. It could be a broken line. There's all sorts of shapes that the Pareto frontier could take. All right, so that was the kind of the simple these are the kind of weighted sum approaches. We either do a standard GA with weights as part of the chromosome, which is a kind of a cheap way to randomize the weights. Or the more expensive way to randomize the weights is to modify the genetic algorithm so it does the randomization for you every generation and you leave the chromosomes alone. So that way you can, in the previous version, you've got giant chromosomes you have to deal with, and it's a little weird to think about how these things are working. But in this case, you're sort of saying, no, these are independent. My weights and my objectives should be independent, so I'm going to separate them out of the chromosome and just modify the GA. But it's still basically the same GA, except we now have this set of non-dominated solutions that we end up finding. So that is class 1. So then after that, people started, and what I'm trying to get, what I like to do when I talk about these, the history of these algorithms, is it really shows the trajectory of scientific discovery and technology, and how we almost need certain bad technologies to get us to good technologies, which in itself is actually kind of a lesson about these evolutionary algorithms to begin with, is that you almost need suboptimal points just to drag you through the space. You know, if you had two fitness peaks that were really, really far apart with no kind of suboptimal fitness peaks in between, you may never have, these two fitness peaks may never find each other. So you almost need these stepping stones that are never actually anywhere close to where you'll end up getting, but they help you find the way. And so in this particular way, you know, people started from linear programming, and they said this is, you know, a linear programmer's way of approaching a meta-heuristic. Linear programmers hate meta-heuristics, and so this was like, you know, they're the easiest way into it. But then that brought more people into it, and they said, oh, well, you know what, there maybe are better ways to do this. And so this was a better way to do it. But then people started thinking about this and said, well, really, if all you're trying to do is switch the selective pressure from one objective to another, why don't you just modify your genetic algorithm to do exactly that? And so that came us up to these kind of class 2 multi-objective algorithms, which are the ones which alternate the fitness objectives. And actually, just yesterday, I was in a lunch with someone who, does anybody know who Rodney Brooks is? He was an MIT professor, big roboticist back in the day. He helped sort of found the company that makes the Roombas. So one of his, when he was a computer science faculty at MIT, one of his students who's now named Carl O'Malley, actually became an MD and got interested in cancer and all that. He started out as a computer scientist, and so now he studies cancer and ecological approaches to approach the treatment of cancer. And they use as a model system the evolution of yeast, real yeast, and he was looking for ways in which to slow down natural selection by applying different benign fitness pressures in sort of random ways. The thought being is that rather than giving someone chemotherapy, you could give them something that's totally benign and then give them something else that's totally benign. If you switch back and forth, then maybe cancer wouldn't be able to keep up in these weird fitness pressures, and it would slow down its own rate. And so it was interesting he was saying that. I thought, well, you know, that's interesting because that approach to me sounds just like these multi-objective approaches that were tried in this family of alternative objective functions. And so the idea here is, so the standard one is Vega, which are these vector evaluated genetic algorithms. And the idea here is they say, well, let's just forget about weights and instead create K subpopulations. Now, what do I mean by K subpopulations? Typically, the way this is implemented is you index your individuals, say x1 up through x n divided by k, all the way up to x n, where n is the population size. And you will end up viewing these batches as a subpopulation. And so this batch is going to have F1 applied to it. The next batch will have F2 applied to it. The next batch, F3, and so on, all the way down to Fk. And so each of these populations is of size n over k size. And so the idea is you're going to apply selective pressure for one of these, and then you're going to basically randomize their order, so give them all new indices. So the next time through, you get a different batch that show up here. And so that's one way to view it. Another way to view implementing this is you've got a little subpopulation, and then there's kind of migration between those subpopulations. That'll get even closer to where we're going to end up at the end of this thing when we get into distributed genetic algorithms and parallel genetic algorithms and multimodal optimization. But so that's basically the idea here, is that I've got K little subpopulations that each are, you run a GA, so you run K separate GA generations for each of the K different optimization objectives. Each one gets a different optimization objective. And then you, between rounds, you then reorder them. And by reordering them, you end up sending those that were selected for one population into a subpopulation that's being selected for something else. So K separate generations with random reordering into new generations between rounds. Yeah.
So in this case, the weights cannot be random, right? It will meet the purpose.
There's no weights in this case.
At all.
That's right. Yeah, we've gotten rid of weights. Yeah.
So if you're like dividing up in these little, we call them like islands, and you're trying to like get better speed in one and then better something else in another.
That's right,
You're
yes.
taking your fastest performers in one population,
Yes.
putting them with your strength performers in another.
Right.
But then how does that make sense? Because it's like mixing athletes among sports. What is the use?
Right, well, so the thought was that if the optimization objectives had the right structure, that if you optimized for speed in one, and then you then put pressure on them to optimize for accuracy or something in the other, that the individuals here, the mutations that would be favored, that would pull them into the accuracy camp, would pull them kind of along the frontier, and they would trade off speed in order to get a little bit of accuracy. Now in reality, unfortunately, this class also suffers from the problem that what you end up getting is not that dispersal across. You would like to get the dispersal across the frontier, but in the end you really do get a clustering up here and a clustering down there, because in most of these cases you don't have this nice structure. You just take, if you take a bunch of individuals here and you subject them to a pressure down here, then the ones who are really good at this stuff are probably just going to die off. And so you end up just getting kind of a reinforcement of these modes, these communities here. So you get kind of a speciation that doesn't really help promote the community diversity. So this was another shot at that, but it didn't quite work so well. Yeah.
Just to clarify, over here every F is a separate objective function.
Yes.
Where we are training according to each of those separate objective functions to for our population, correct?
Training. Well, I guess that's
Not training, meaning that we're running our separate genetic algorithm
That's right.
for each
Right.
separate.
Mhm.
But then how do you, so at the end, like for example, you reach run number 100, which you have set as your end.
Yeah.
At that point, you take the fittest individuals from all of these subpopulations?
Oh yeah, so good. So usually the way these things work is that you run a full generation inside for one subpopulation. So you're going to have like an expansion and selection. All of that's happening within this one. So in the end, you start out with end individuals, and within the subpopulation, you get selection for the N over K sort of best individuals, or you can think of that as the parents plus the offspring. So it's a standard GA, but then those K, N minus K sized populations just get added together and concatenated. And that ends up being the population that ends up being the output for this. And you can add elitism to this, you can try to look for non-dominated ones and hold on to them. You can add some local search if you want. There's ways to kind of optimize on top of this. But yeah, inside each subpopulation, you just forget that you're in a multi-objective and you just run a standard GA. Okay. All right, so that's vector evaluated GAs, and they still kind of have this problem here because they're not directly addressing the diversity. Everybody in both of these cases is just hoping to get diversity for free, and that's kind of been the problem here. So that's when we kind of got to finally the third generation, which is really where we are currently sitting. There have been advances. There's a nice paper that I have in this module on Canvas, which compares like all of the multi-objective, well, a large set of multi-objective genetic algorithms across time, and it puts them in a grid. And you can see like all of the ways in which they enhance diversity and all of the ways in which they do selection. And you can kind of see that the latest in multi-objective optimization is NSGA 3. That paper goes up to NSGA 2. But basically the way in which they do the pushing everyone to the frontier is now this class 3 that I'm talking about. And now where people play around is with the diversity element. So we kind of have figured out how to get onto the frontier, and now we're just sort of improving the diversity part. And so that comes to this class 3, which is the so-called Pareto ranking approaches. And so with Pareto ranking approaches, the kind of in a nutshell, all we're going to do is we're going to, yeah, I'm sorry.
I have a question. Why don't we, if we found like two solutions that are on the other sides, why you cannot take like a complex combination and that's it? Because it cannot be aligned, right?
Two solutions, so when you say two solutions, you mean if I find, you mean
yeah.
like one here and one down here?
Yeah.
Well, if you say like, well, what am I going to do? Like, if I just mix these two, like, you'll be mixing in decision space, not in criteria space.
Okay.
So if you just do a convex combination in decision space, the X space, that may end up providing you a new X that is off the frontier.
Oh, it doesn't, okay.
Yeah.
Oh, because these are just the functions or just putting
This is like criteria space.
Yeah, makes sense.
Okay.
Thank you.
Yeah, well, that's a good point. Maybe I should make that clear that this is like f of x. Okay. Great, good question. All right, so Pareto ranking approaches, in a nutshell, we are going to rank individuals by some proxy for how many individuals they dominate. So for every subpopulation, we count up how many individuals does this one dominate, and then based on that, we sort of then use that as a fitness function. And so ideally, we would like to make individuals dominate more, and so we are going to promote them. So we're going to create a fitness that is based on how many individuals you're kind of ahead of for that one subpopulation. And then you can recalculate fitness in terms of the ranking for the next one further on there. So if I were to write that down here, just to have a record of that, we're basically going to rank individuals by how many other individuals they dominate. And so if you want to picture that, in that F1, F2 space, where it's better to be bigger in both F1 and F2, and if I had a bunch of individuals just kind of scattered along this, so maybe I've got one up here, I've got one down here, one over here, one over here, one over here, then I can ask for each one of those. Like for this one, I look and they're everybody. It's kind of hard to tell, but everybody is better in well, so this one is maybe slightly better in F1. But, so if I was to, this solution here is better than, I'm going to put a square around it. This solution here is better in terms of F1. It's a little worse in terms of F2. So comparing these ones, it's not clear which one dominates which. But if I instead look up here, this solution is better in F1 for both of these, and it's better in F2 for both of these. So this solution dominates 2. These solutions dominate 0. And so you can imagine, so then this one here, I can kind of do that same game, and I might need to draw dashed lines down from here and see. So if I were to create, let's say, another one, like say out here, a solution out here, this solution out here dominates all of these, 1, 2, 3, 4, 5 solutions. So for each one of these, I can count how many solutions they dominate. Yeah.
So, is this equivalent to like constructing a directed graph where each solution is like pointing to every solution it dominates, and then like looking at the levels of this graph, and like so you take the first level where nothing's dominated, and the second level, would that be equivalent?
Yeah, absolutely. You could think of it like that, and then you can kind of imagine that you're going to have individuals that have the same rank are not going to be in the same. This graph isn't like a tree, but so you can kind of think of them being sort of off on the side, and so yeah, you definitely can have kind of another graph theoretic perspective here. But in the basic idea here is that what you're forming are level sets in like a weird space, because it's not like I can draw lines like this is, or like Euclidean space where I could say like, this is some distance from the origin, this is a little bit more from the origin, and so on. But I am kind of creating something which is a distance from the origin. But exactly how I'm weighting the distance from the origin kind of depends on how many solutions are here. But so it sets up a kind of a discrete distance from the origin. And we would like to maximize that discrete distance from the origin. So out here, I've kind of got everybody who's 5 or better. And then, as you move down this way, so you can kind of think of that each one of these solutions has kind of got a cone above it. And like this solution will be dominated by any solution that's in that cone.
So like, is that?
I'll get.
Yeah. So how do we rank the individuals who do not dominate any one of them?
Well, if they don't dominate any, they get a 0.
So how do we rank among them?
Oh, well, that's a good question. So you would just assign them a similar fitness. Like these are like 2 solutions that just happen to have the same fitness. And that's the beauty of it, is that we are putting pressure that moves us toward the frontier without putting pressure about where we are on the frontier. Yeah.
Is ranking gonna trace out some kind of a contour, like a well-formed contour, or?
Well, that's the contour that hopefully the ranking will converge to will be that Pareto frontier. Now, whether I get this nice surface, like these nice level sets, like that's kind of, this is sort of a temporary way to rank these things, and every time I re-rank them, then like you get a new population that shifts higher and higher and higher. But the thought is that with increasing pressure in this direction away from the origin, then I will converge to whatever the shape of is this Pareto frontier. And everybody along that Pareto frontier will end up having the same rank when I get there. So you can think of there's some weird contour of iso rank that we're trying to walk up. Yeah. So you could so basically this you could say there's 2. I mentioned this is one way to rank them. The other way to rank them is to say, all right, I've got my set of solutions. Remove the non-dominated solutions and assign them. So this rank is the one where you want to be highest. The alternative way to rank was to take your set, remove the non-dominated solutions, and give them an index 1. Now you've got a set of everybody else, but there are non-dominated individuals inside that set. Give them rank 2. Then remove them. So that's the other way you could view this, is that instead of ranking them in terms of how many they dominate, you could rank them in terms of what round of this removal process were they removed. And so in this other alternative, I would remove this one first, and then I'd be left with these. And then these 2 would be the non-dominated ones, and so they would get removed next. And then these 2 would be the non-dominated ones, and they would be removed next, and so on and so forth. And so, you end up getting basically rank 1, 2, 3, so it just changes the ordering of these things. But again, as talented computer scientists, you might be able to come up with clever data structures to make this process more and more efficient, depending on how you do this. But multiple ways to do it, but the whole idea is you're trying to give everybody who's non-dominated the same rank and everybody else a lower rank. And if you happen to be kind of closer to the non-dominated ones, you somehow are going to get more or less of a penalty than the others. Yeah.
Is each dot on the diagram meaning both F1 and F2, or it could mean only one of those?
Well, there's not a meet. This X here means that there is some individual that scores this much in F1 and this much in F2. And so it isn't that they're meeting a criteria or anything like that, but that's just the property of this individual, that they're this fast and this accurate. This individual is both slower and less accurate. This individual is both faster and more accurate. This individual is more accurate but is slower, and so on.
The point is, if I understand correctly, then every point, zillions of them, right?
Mhm.
But,
That's
so-
right.
Right?
Yeah, there's zillions of points, and they all would end up getting a rank.
So how about the efficiency of the algorithm?
Well, again, that's so there's a lot of, this is where things like sorting algorithms and things like that end up becoming useful, is that this is an ugly problem, which is the reason why we use meta-heuristics to solve it. So we try to use a small subset of individuals and hopefully move those individuals around the space in kind of a sparse way that gives us the greatest shot of finding this Pareto frontier. Brute force to find this frontier might be really ugly because you would have to evaluate all these pairwise combinations. So I already got to figure out how to enumerate this space, and then once I've enumerated this space, it'd be a really a mess. And that's what here, we're trying to come up with a clever way to sample from the space so that we get closer and closer to this line, so that instead of sampling from the whole space, we end up just sampling from the line.
But one point doesn't push me towards a better point in this.
Well, it pushes me toward the line, but it doesn't. So far, this level, I haven't told the rest of the story, but this half of the story pushes me toward the line. How that I deal with spreading myself along the line is the next half of the story. But so this makes sense, this idea of ranking approaches, and you can rank by how many you dominate, or you can rank as to when you got removed as a non-dominated from the set. So the two kind of common ways to do ranking. There are other ways to do ranking, but they all kind of are some proxy for this. Okay, so that helps move me toward the Pareto frontier, wherever it is. But now I want to sort of make sure that they aren't all moved to the same point on the frontier, which may happen by chance. So there are a bunch of mechanisms for maintaining diversity, and the simplest mechanism is so-called fitness sharing. And the idea here is borrowed from this idea that I'm trying to create niches. And my idea is if two solutions are in the same niche, they're going to be competing for that niche. And so they really have to share fitness. So how do I deal with that? Well, if I basically could create little bubbles of solutions that are close to each other, either in criteria space or in decision space, then within that bubble, I am going to divide all of their fitness by the number of individuals in that bubble. So there are kind of two ways to do fitness sharing. Is if I've got my Pareto frontier here, for example, well, I actually don't know where the frontier is, but right now I've just got a bunch of points. Some are up here and some are down here. And in criteria space, I can say for every point, I am going to draw a circle. Maybe when I'm evaluating the fitness, I am going to pick a point and draw a circle around that point in, say, criteria space. So this is my F1, F2 criteria space, not decision space. And anyone inside this sufficiently small circle, I am going to divide their fitness, whatever it is, so their Pareto rank, for example, by the number of individuals in that bubble. So, so here I would say divide each fitness by 3. And if I took that same size bubble in a different part of the fitness space, then I might divide by a different number. So if there's 4 in here, so divide fit by 4. And so the thought here is if you got some clustered together, then it is going to be very likely that some combination from that group is going to survive if the group as a whole has a high fitness. but we're not gonna allow all of them to survive. Because if they all have high fitness and they're all close together in this criteria space, then we don't need to sort of just to duplicate all in that area. So we're gonna make sure we have some representatives from this niche, but we're not gonna allow this niche to send a whole bunch of representatives just back to the same niche. So we're effectively assigning fitness per niche, but we have to we don't know what the niches are, so this is sort of an unsupervised way to cluster these niches, come up with where these niches are, and then spread the fitness within the niches across everybody in the niche. Yeah.
Well, one of your parameters is the size of the bubble.
That's right. That could be a hyperparameter for these things, is the size of the bubble. There are a number of different ways to come up with how to draw these bubbles. There are kind of ways that are more discrete in nature, there are ways more continuous in nature, but all of them have the general feeling. It's kind of like setting up some kernel on a kernel density estimator or something like that. There is some bubble that is that your selection algorithm uses to calculate fitness. And as it sweeps down through here, whenever it finds an individual, it's going to scale their fitness by ever how many individuals are around them within that little kernel. As it slides. Is there a question, John?
I'm just trying to understand why dividing by the number of individuals is actually reducing how many of them get put back in that niche.
Well, it's not, it's sort of turning them all into the same strategy. And so if we had, instead of having 3 individuals, like these 3 individuals are close together, and it might just be that they all have a high fitness. And so their fitness might just happen to be higher than everybody else's fitness. And so if we allowed fitness by itself to drive things, then everybody here would be washed out and we'd just be stuck with these individuals. So now we're saying we already discovered this part of the niche, so we're gonna divide it by 3, and that's gonna kind of give these individuals a chance to stay in the population. Now that might mean we're gonna lose this one, but that's okay because this one's basically identical to this
The
one.
other one. Gotcha, so it's like encouraging exploration throughout more of your.
That's right, it's slowing down selection. So yeah, all of that stuff about mutation, selection, drift, it definitely applies here. So we want to slow down selection, and we do that by effectively scaling fitness. Yeah.
Can the bubbles overlap?
Well, yeah, so with this kind of kernel thing that I was talking about, then yeah, the way you do that, like you could say, well, I'm gonna pick an individual and then I'm gonna scale everybody by 3, and if I've already done it to them, then I just jump, I skip these individuals. Or I can imagine this continuous kernel that as I'm evaluating fitness, I like put this umbrella around you and I figure out how to scale your fitness, and then I put another umbrella around you and scale your fitness. And so, and that might be the easier way to think about it, is that like when you figure out the fitness of every individual, you then throw out an umbrella, see who else is under that umbrella, and then divide that individual by whoever else is in that umbrella. When you go to the next person under that umbrella might include a whole lot more because it's just kind of skewed that way. So that is, but you can imagine a bunch of different ways to skin this cat. And ultimately it's just basically this idea that if there are individuals nearby, you will share your kind of communal fitness, or at least your fitness will be divided by however many individuals are by you. Yeah.
Can you think of this fitness sharing is one kind of selective pressure because the leftover bubbles, because they just containing 3 individuals, they divide by just 3. But down the right, the bubbles just only 4. This means that the leftover just move down right the bubbles. It has a little fitness values, right?
Absolutely. I think you could definitely view this. So the comment here is that if you happen to be down here in an area that is underexploited, then you will have less of this penalty.
Yes.
And so it's almost as if we're rescaling. So this acts as a new. What is a selection pressure? A selection pressure is something that puts an undue cost on. Well, it's not to say undue, but it puts an extra cost on some individuals. And that's exactly what this does. You're saying to this individual, I don't care how great you are, you've got so many individuals around you, I'm gonna put an extra penalty on you. Down here, you'd say, oh, well, you don't have anybody else around you, so it's almost like you're amplifying them. So that's another way to do it. It's like we've taken selection pressure that would be only in this direction, and we've spread it out to also be in this direction.
It's like a communistic idea.
Well, I think that that would be a difficult interpretation, or at least it would be. I think there's a lot of points to get from here to there, but maybe if that helps, then go for it. Yeah. Is there a question in the back? I thought I saw a hand.
So basically what we are doing is, maybe within a bubble, we are reducing selection pressure, but on the population as a whole, we are eliminating selection pressure so that we don't converge way too soon, and you guys can reach at that same Pareto frontier, but in different ways.
That's right. It's selection shaping. Yeah, we're reshaping the selection pressure. Just like in signal processing, we have noise shaping because we have to deal with the noise, so we may as well put it in high frequency. In these things, we're going to have selection pressure, so we may as well put it at in the spots that are underexploited. Yep, absolutely. All right, so. And that's basically, most of these Pareto ranking approaches are going to have those two components. They have some way to rank the individuals and some way to dispense them. Now, an alternative way to do fitness sharing, which we'll talk about a little bit more maybe later, is that you could alternatively, instead of dividing the fitness, you could just kill individuals. You could say that if there's 3 individuals in a bubble, I'm going to choose one of them at random and eliminate them from the population and then redraw someone else from the population. So that is another way, kind of a negative selection way of doing it, is that even though you've survived to this high fitness, because there's so many else around you, then we're going to use that as an opportunity to bring new individuals in the population. So you get all of your fitness goes here, and your 2 fitnesses go to 0, and new individuals come up. So that's the other way to do this. All right, so let's see where we are. Yeah.
One thing, like each of the population is gonna have different fitnesses, right, along each of the axes. I mean, each of the things that we're gonna optimize, like if the variables are x1 through xn, and we're gonna have f1 through fn for each of the individuals.
There's only one fitness. Fitness is the fitness in here is the rank of the individual.
Yeah, well, like along one axis.
No, there's only one. The fitness axis is basically this oblique axis, and it is the Pareto rank. Each one of these F's, these are just our criteria. These are just characters of the phenotype. These are just different ways in which we can evaluate. It is true that I can subjectively say I would like more of this, or all things being equal, more of that. But the fitness that the genetic algorithm sees is the Pareto rank. And so at that point, we've washed out all of the criteria and we've replaced it with a single value, which is their rank.
Yeah, and it's gonna be the linear combination of each of these functions?
No. Well, in class 3, in my Pareto ranking approaches here, then it's not a linear combination anymore. It's just how many solutions do you dominate. So every generation, you calculate this number, and that ends up being the pressure which moves you from one generation to the next. But this linear combination interpretation doesn't apply to really from class 2 to class 3, we got rid of linear combinations. So it's this more abstract thing.
Then are these numbers that we assign to them the fitness values?
Yes, that's right. The Pareto ranking ends up being the fitness values. This dominates 5, so it has a fitness of 5. This dominates 2, so it has a fitness of 2, and so on.
And then like we basically do not have a bubble, right? We have like as you said, like an ISO fitness curve kind of a thing.
You're right, and actually, in the kind of the ultimate ISO fitness curve is the Pareto frontier itself. And so anyone laying along the Pareto frontier has kind of equally high fitness. And you can't go any higher than that. That is the maximum. That is the global optimum. And now, if you want to spread along that, that's what I'm saying is that we need to create a fitness component that is tangential to this. So we do need some spreading fitness component to provide this pressure here, and that's what fitness sharing does. So we've reduced fitness to a single dimension, and then we've reintroduced fitness that is sort of orthogonal to that dimension, and that's what fitness sharing is doing, and it spreads them out. So we've got primarily moving them up and a little bit of spreading them out, and then hopefully that then spreads them across there. And so if you were to go to like if you were to do like help on GA multi-objective in MATLAB, for example, then you basically find, it'll tell you how that algorithm works, and it is, I mean, for all, you know, rather than writing it all out, it's effectively just, you go up to a certain number of generations, and you do proportional selection based on rank, and then you do single point crossover, mutation, then you evaluate your K objectives, calculate your ranks, do your niche counts, and then you can do fitness scaling if you'd like. So this was a strategy that we mentioned briefly in normal GAs. You can scale fitness if you want to kind of reduce the fitness pressure, and then you do fitness sharing. And that's just, you know, so there are certainly more sophisticated multi-objective optimization algorithms out there. Like I mentioned, state-of-the-art from a group at Michigan State is NSGA2 and NSGA3. But if you just go to sort of like, if you say, you know, a commercial engineer who needs to do a multi-objective problem, goes into MATLAB and types in GA multi-objective, and basically the algorithm here, although you can certainly modify these things, out of the box, the algorithm is exactly the picture that I just drew for you. It's just rank by fitness, select, you know, use that as your main selection pressure, and then do some fitness sharing to spread out. And that's it. That's basically the modern day multi-objective genetic algorithm. So any questions on that? All right, so the last couple minutes here. So some other things that, so you know, once people started thinking in this way about these multiple fitness objectives and promoting diversity and different ways to promote diversity, then it got people thinking more and more about how to revisit the original genetic algorithm and improve diversity there, using everything that they learned about promoting diversity in these things here. And so when they realized they had to create the notion of a niche, the notion of an island that allowed things to kind of work on its own and then occasionally be influenced by the other islands, then they realized that maybe we can go back to the normal genetic algorithm and improve the diversity, and maybe end up actually improving the way in which it searches through a single objective space. And so it's this kind of interesting progression where you go from GA to MOGA back to GA, where here I'm going to call it the multi-modal optimization. And multi-modal optimization basically is a way for the GA folks to get really kind of, it's a little bit of hubris here, because they're saying in the GA it was a global optimizer. They're saying we are going to do our best to find the one optimum point and not get stuck in a local. And then MOGA, we all know what that is now. And then they went back and the multimodal people said, wait, maybe we can actually find all of the optimal points. So not only the global, but all of the local. And so that is sort of their way of saying that in the GA, our population was just kind of a waste. It was used kind of in the transient case, but we only looked for one solution. And in the MOGA, we needed a whole bunch of solutions. So then in multimodal, they said, let's figure out a way to take the GA and actually make use of those multi-solutions. So now our objective is to provide a population where that population describes all of the local optimizers. And that's the goal behind multimodal optimization. Yeah.
I think I'm just lost into where you'd apply that, because if you can find the global, why are you also trying to get the locals?
Well, so I mean it could be an interesting, it could be a good, a good question here, but there might be application spaces where it might actually be not an optimization. It might actually be like I'm doing something where I actually need to do peak detection or something like that. So how could I use a genetic algorithm to find all the peaks? And so that's, so there could be a lot of different reasons why you might need to find these multi-modes. It's my claim that genetic algorithms are strongest here in the middle, that they're okay here, but there actually are other metaheuristics that are better than genetic algorithms. And here is a little bit contrived, but is interesting, but it's here is where they really shine. And so, so that's why, but I think we don't talk about the multi-objective because it's just a weird thing to talk about. But that's like, I view that as the real selective pressure that brought GAs into existence, or something like they got brought into existence here, but then they found this niche and they just exploited the hell out of it. So, but so people went to multimodal, and so the question was that how do you provide this level of diversity searching to this type of problem to help ensure that you're able to actually not just guarantee that you find a global, but that you kind of spread yourself around the entire space to find all the locals. And so people then started doing kind of these crazy things, and so island models came up. And what was interesting about these island models, and these are you can kind of actually view as Vega-like, is that what if we take my population of M individuals and I divide them arbitrarily in K groups, where each group evaluates the same objective. So I've taken a large population, which I always said was good because it gets rid of drift, and I've now made that population smaller and had them evaluate these optimization objectives separately, and then periodically allow individuals to mix from one island to another. So I have a little bit of migration between these islands. So what was interesting, so same objective for these K groups, is that people found that by doing this structure, one thing they could do is they could now parallelize the genetic algorithm even more. So before, you could have every individual can be calculated, fitness can be calculated in parallel, but it's a little bit of a hassle to distribute a single solution to a core or a whole nother machine on a network just to calculate some optimization objective. And so, but here you can actually run K independent genetic algorithms in parallel with each other that only occasionally talk to each other. And so it has that nice architecture. And the weird thing they found about it is that this thing had a better exploratory properties than running a GA with a single M here. So somehow it defeated the problem of drift, where a small population, M divided by K population, if you just had a small population, you wouldn't be guaranteed to get even anywhere a good solution out. If you had a large population, then you might end up converging to a local optima and you get stuck there. You wouldn't be able to explore enough. So you could up your mutation rate, and this sort of had this weird effect of acting like a hypermutation or an adaptive mutation, where suddenly you could find these global peaks. And we're going to pick up there next time, but what's cool about this is, if you're interested in reading ahead, is that there's this famous population biologist named Sewall Wright. And Sewall Wright was obsessed, or was interested in the idea that there could be adaptive valleys that you could never get through because you pay such a fitness cost to move from one peak to another that you would never climb between them. And he came up with this thing called shifting balance theory, which would be, what if you could isolate individuals in small populations and occasionally migrate between them? And in theory, then you could actually end up crossing these adaptive landscapes. There's been no evidence that this actually is useful in biological systems, but this appears to be exactly what's happening in these distributed genetic algorithms. So here you've got a theory from biology that hasn't really helped biology one bit, but it perfectly describes what's going on in this evolutionary system, which I think is kind of interesting. That's all I got for you today.